Okay, hello everyone. I'm presenting Evaluating Model Explanations Without Ground Truth. I'm Kai. This is joint work with Zihao and Eoin, who couldn't be here, and supervised by Professor Chris Russell. A TikTok overview, because 9 minutes can be really long to pay attention. So the same prediction can have different explanations depending on which method you use to generate that explanation. In such a scenario, it can be hard to measure which explanation is the best, which one to use. So we propose a new method called AX, which you could use to measure the quality of competing explanations. AX stands for Ground Truth Agnostic Explanation Evaluation Framework. It's intuitive. It can detect fair washing in explanations. We learned a little bit about this in the previous presentation. And you can use AX without having access to a ground truth explanation. So you don't need to know what the correct explanation is for a prediction, and you can still use AX to measure explanation quality. Our code is on GitHub. We would like if people use it, so please do that. Before I get into AX, just an overview of what an explanation is for the purposes of this presentation. And that's different from maybe what we'll see in the next few presentations. I see there's something about prototypes. We are dealing exclusively with feature importance explanations, which produce this kind of signed vector, which tells you how important a particular input variable was to a model prediction. And we're also only dealing with local explanations, so not interested in explaining model behavior holistically or overall model behavior, but just one particular prediction. There can be many explanations for one prediction. Here's a diabetes prediction model that says that a person is likely to have diabetes. You use SHAP to explain why that is, and it tells you it's because of the glucose level. You use LIME, and it tells you it's because of both glucose and BMI. And you use just the gradient of the logistic regression, and it tells you that it's because of diabetes pedigree function. You can see that these conflict. This disagreement has been well studied in the literature. So yeah, that's a clear conflict between these explanations. So now when we want to evaluate these competing explanations, what do we want to do? For the purposes of this paper, an evaluation is a scoring function of the input vector x, the model m, and the explanation e. When I say scoring function, I mean that this function should give me a single score as an output, and then I can compare different scores to figure out which explanation to use. So I want to measure which explanation is best, and the short answer that we use in this paper is that you should use the explanation which is most predictive of the model output. So just by looking at the explanation, if you're able to sort of guess what the model output must have been, then that's the best explanation. The slightly more nuanced answer is that your explanation should follow these three principles which we propose: local contextualization, model relativism, and on-manifold evaluation. In detail, local contextualization is motivated by the fact that an explanation should reflect that a model is not always constant across all inputs. So for different inputs, you get different model outputs. This means that when the input x changes, your evaluation might change. You should not expect the same explanation all the time. The second principle is the same thing applied to the models. So the explanation should depend on the model. If I change the model, the explanation probably changes. It shouldn't always stay the same. And the last principle is on-manifold evaluation. This reflects the fact that many explanation methods work by sampling points in the neighborhood of the input x. And we want our explanations to actually only be a function of this input x. And if I change behavior on these off-manifold data points, I would likely not want the explanation itself to change. So the evaluation should be independent of this behavior off-manifold. The key idea behind AX then is to select the explanation that best helps predict model output. The way we do that is by using this nearest neighbors model on the subset of features deemed most important by any given explanation. There are many ways to define this, and we use one particular instantiation, not because it's the best, but it's because it's the first one we came up with. So happy to hear any mistakes here or things that could be better. I'm not going to go into the algorithm in detail, but happy to talk offline more about it. It's fairly straightforward. The key idea is, as I said, to construct a nearest neighbors model, one per data input point, and the model only uses the features that have been deemed important by any given explanation. Now, detecting explanation fair washing. This is something that Axe enables quite seamlessly. A great background provided by the previous presentation about what fair washing means. Here we use an adversarial attack that deliberately sort of modifies explanations to seem benign, even though the underlying model is known to be discriminatory. And then we compare different explanation evaluation techniques to see if we are able to recover the fact that these were really poor quality explanations. Ground truth-based metrics are unusable in this kind of scenario because you don't actually know in the real world what the ideal explanation is when you deploy a model. That's something that either you need to assume or you need access to some kind of oracle. So those metrics are often a non-starter. There are other metrics that work without ground truths, PGI and PGU. These stand for perturbation gap on important and unimportant features respectively. But these are susceptible to this kind of attack, and they don't always detect fair washing. Axe is completely invulnerable. This is like theoretically true. It cannot be deceived by this kind of adversarial attack. So it is able to detect when an explanation has been fair washed or adversarially modified with sort of perfect recovery rate. So why do we think people should use Axe? Well, it's principled. It's the only explanation method that I know of so far. Again, please come correct me if I'm wrong about this. That follows all three of these principles. It's pretty robust to any hyperparameters you can vary in this in the algorithm. We show this empirically. It detects fair washing with sort of perfect accuracy, like I showed in the plot on the previous slide. And it's really cogent. And this is quite important in the sense that a lot of previous explanation methods, including like ground truth-based methods that are comparing with an ideal explanation, actually end up rating a completely randomly generated explanation with like arbitrary feature importances surprisingly well. Those are really randomly generated explanations. You want them to have poor scores, but they often don't. That's not the case with Axe, as we show empirically in the paper. So yeah, so that's Axe. Thank you for your time. Here's the code, slides, paper. Yeah, happy to take any questions. Thanks.